Hello, everybody. My name is Rhys Paterson, and I'm a master's student at the University of Western Ontario. I'll be talking to you today about my thesis, the subsurface correlation of the lower Silurian Medina Group in southwestern Ontario. This study builds upon efforts by the Ontario Geological Survey and the Geological Survey of Canada to update the lithostratigraphy of southern Ontario and to provide an improved regional stratigraphic framework of the mixed siliciclastic and carbonate units that comprise the lower Silurian Medina Group. Despite the long history of study of these classic Paleozoic successions, there are several important questions that remain to be resolved concerning stratigraphic nomenclature, distribution of various units in the subsurface, and regional extent of marker horizons. The lithostratigraphic chart on the left, which we are all familiar with, graphically depicts the disconformable nature of lower Silurian stratigraphic units across southwestern Ontario. The Medina Group, as shown in the lower right graphic, displays the current stratigraphic usage adopted by the Ontario Geological Survey and includes the following formations from oldest to youngest: the Whirlpool sandstone, the Manitoulin dolomite, the Cabot Head / Power Glen shales and mixed silty shales and carbonate lenses, the Balls Falls dolostone and Devil's Hole sandstone, and the Grimsby and Thorold sandstones. The main objective of this subsurface-focused master study is to integrate lithostratigraphic observations from cores and cuttings with borehole geophysical profiles. As well, combine and include information with the identification and delineation of key marker horizons, i.e. phosphatic lag deposits and faunal units, and previously undocumented occurrences of the Balls Falls dolostone and Devil's Hole sandstone units in the subsurface. With the combination of this information, an attempt is made to update the regional distributions and therefore can be included in future stratigraphic studies or it can be used for future exploration in Ontario. Let's meet the main formational rank team members of the Medina Group from bottom to top. The Queenston, though not part of the Medina Group, is discussed in brief due to the contact of the above Whirlpool Formation. It's described as red maroon to gray-green shale. The Whirlpool Formation is described as white to gray to tan, fine to medium sand grade quartzose sandstone with dark and or light gray shale interbeds and laminae. The Manitoulin is described as microbial laminated green calcareous shales grading upwards into both thinly bedded, muddy to skeletal dolostone beds. The Cabot Head Formation is described as gray, green to red maroon, non-calcareous shales with subordinate sandstone and carbonate interbeds. The Power Glen is described as dark gray to greenish gray, sparsely fossiliferous marine shale with interbeds of sandstone in the upper third of the formation. The Devil's Hole Formation is well sorted, white to very pale pink, slightly dolomitic, medium to fine sand grade quartz arenite with some horizontal to hummocky cross stratification with minor interbeds of gray-green shale. The Balls Falls is described as thin beds of dolomitic sandstone, fine-grained dolomite, and interbedded gray to red shale with hematized sandstone beds. The infamous Grimsby is described as interbedded red and green sandstones, siltstones, and shales. And the Thorold, described gray-green to white, fine to coarse grade, sand grade, quartzose sandstone with minor thin gray to green shale or siltstone partings and shale interclasts, and marine trace fossils are found as well. Now that there are descriptions of the defining characteristics to the main units found, what does it look like using those descriptions and picks across the study area? This slide shows 47 key gas wells chosen to provide a regional perspective of the Medina Group. Primary and secondary wells were chosen based on most complete core and cuttings coverage and accompanying geophysical logs. 2 cross sections were then completed. A to A prime, seen in the black line running east to west across the study area, combining fence post wells and primary wells across Lake Erie with the most geographical extent. B to B prime runs perpendicular to A prime, concentrated in the west of the study due to availability of core. The base of the Medina Group is the Queenston Whirlpool contact. A familiar boundary, the contact between the Whirlpool and the Queenston is fairly sharp, planar, and contains abundant green shale rip-up clasts from the top of the Queenston. On the left, core 1001, located in the west, has a little bit of Queenston, seen in red, a thin bed of Whirlpool, seen in blue, and transitions upwards into the Manitoulin, seen in green. Core 229, located in the east, has Queenston, seen in red, and 3 distinct depositional lobes of the Whirlpool Formation, seen in blue. Below is a close-up of the contact between the Queenston and Whirlpool in either core. The Whirlpool Formation is gradationally overlain by the Manitoulin Formation west of Grimsby and by the Cabot Head / Power Glen formations east of Grimsby. Again, 1001 to the west and core 229 to the east. In core 1001, you can see the close-up of the contact, slightly gradational from the fine-grained sandstone to fine-grained dolomitic sandstone. To the east, core 229 is visible from the change in white fine-grained sandstone seen in blue to the dark gray shale of the Power Glen seen in orange. Regionally, the Whirlpool is mappable as far as Hamilton, Ontario, but there are thin intervals preserved further onshore. It undergoes facies changes, grading into a carbonate facies of the Manitoulin dolomite. The introduction of the Power Glen shale is to the east around Haldeman and core 229. The contact between the Manitoulin Formation and Cabot Head Formation is gradational. To the west, with more lime-rich sediment, there is a presence of greenstone beds within the dolomitic shale, as you can see in the close-up in the bottom left. To the east, the sediment is sand-rich, resulting in more silty shale packages within the dolomitic sandstone beds. The contact between the Manitoulin Formation and Cabot Head Formation is gradational. To the west, with more lime-rich sediment, there is the presence of greenstone beds within the dolomitic shale, as you can see in the close-up in the bottom left. To the east, the sediment is sand-rich, resulting in more silty shale packages within the dolomitic sandstone beds. The core photo of 999 is to the west, and the 2 photos to the right are 371, located centrally to the study area. Core 999's Manitoulin Cabot Head contact is difficult to delineate. There are abundant dolomitic beds, grainstone to waxstone beds interbedded with shale. The use of the geophysical logs is necessary to confirm the pick between the Manitoulin and the Cabot Head shale. Core 371's Manitoulin Cabot Head is much more distinct, with a change from dolomite and shale to a tighter, more fissile shale at the base of box 10. Core 1001 to the west and core 173 to the east, Devil's Hole is laterally traceable across the study area. The Devil's Hole Formation was once considered part of the Grimsby as well as the Power Glen and Cabot Head. There are issues with correlation due to the similar characteristics between facies. In this study, the Devil's Hole is picked with the first occurrence of a large white to yellow fine-grained sandstone found within the dark gray shales seen in red. This contact is gradational with the underlying Cabot Head Devil's Hole formations seen in blue. Duke and Brett's definition of the Balls Falls member consists of thin beds of dolomitic sandstone, fine-grained dolomite, and interbedded gray to red shale. Locally, the sandstone beds are hematitic and stand out as deep red beds in an otherwise greenish-gray Power Glen shale and basal Grimsby Formation. Core 103 is located centrally onshore Ontario, showcasing the dolomitic sandstone and deep maroon sandstone beds of the Balls Falls. Core 337 is located to the west, showcasing Devil's Hole sandstone seen in red, and in the middle we see the maroon fossiliferous dolomitic sandstones interbedded with the shale seen in blue. These latter 2 units have previously only been recognized and named informally in outcrops between Balls Falls and western New York State in a 1987 and 1991 field guide and in the United States Geological Survey's subsurface correlation study. The Devil's Hole Grimsby contact is unique to say the least. The change from sandstone to sandstone has an interesting boundary, the presence of a phosphatic leg. The Art Park phosphate bed can be correlated across the United States and in southern Ontario is an indicative of a hiatus. My contribution to this description of this formation is the addition of the Biozoan-bearing calcareous and non-calcareous mudstone beds considered part of the Cabot Head Formation by Sanford and other geologists. Core 173 unfortunately shows a gap in core, but below shows an interesting transition between the dark shale and sandstone of the Balls Falls seen in blue, below the characteristic Grimsby sand above seen in red. This can also be seen in core 341. The next contact is between the Grimsby and the Thorold. To the east, 173 shows up in the contact between Grimsby and Thorold near the top of the box of box 52. Core 386 has a clear Thorold Grimsby contact. The Thorold has interbedded gray-green shale and sandstones with abundant bioturbation, while the Grimsby has pale pink sandstones and maroon shales with significantly less bioturbation. The final contact is the Thorold with the above Clinton group. There are varying formations that touch the Thorold, though they are not defined in this study. Usually the Clinton carbonates are a dedicated signature on the geophysical log that make the pick easy. Things like the Rockway, Renales, Meriton, and Neohaga are all formations that border the Medina. There is also the presence of another phosphatic lag, the Densmore Creek phosphate lag, that also can be seen in some cores. Core 1001 showcases the contact between the Clinton carbonates and the Thorold Formation with a heavily bioturbated bed. Core 173 shows a different contact, tan, green, fine-grained sandstone with a sharp contact with the Neahaga shale above. By combining the refined picks, we can then conceptualize the distribution of the contacts in a cross-section. In entirety, we see A to A prime and B to B prime. The cross-section is hung from the bottom Queenston Formation geologic pick. A to A prime runs west to east, starting with core 766, consumers 13755, Lake Erie 220W4, and ends at core 173, consumers 32271, Wainfleet 223. In general, there is a thin bed of Whirlpool continuous across all cores seen in dark green. The Manitoulin Formation pinches out as you move eastward, seen in light green. The Cabot Head, Power Glen changes in thickness east to west. The Devil's Hole changes in thickness as sediment availability becomes apparent in the east. The Grimsby Formation also changes with available sediment, seen in pink, while the Thorold drapes thinly over the Grimsby with a contact with the above carbonates serving as the top pick. There are some noticeable red lines within the Grimsby, designated the presence of the Birozoan beds considered to be Cabot Head by previous geologists. There are thin blue lines to designate the phosphatic lags that are found in the core. These phosphatic lags can be diagnosed as the Art Park phosphate lag across the study area. B to B prime runs north-south, perpendicular to A prime, and starts with core 999, consumers Pan Am 13057, Lake Erie 56E3, and ends at core 1062, Pembina Central, Lake Erie 184I2. There is a general thickening of sediment towards the south. The Whirlpool and the Manitoulin formations are fairly planar with some slight changes to the Cabot Head. The availability of sediment of the Devil's Hole influences the thickness of the Grimsby, while the Thorold is very scarce. The geophysical logs show the Clinton carbonate's classically shaped signature designating the top of the Thorold. By combining cores, cuttings, and geophysical logs, refining and redefining previous geologist picks, and using that information to show lateral changes within the units, we have come to the final part, the conclusion. There are 4 distinct packages of rocks that are to be studied. The Whirlpool Formation, the story of the upper versus the lower Whirlpool and how it interacts with the Queenston. The next is the Cabot Head, Power Glen, Devil's Hole story, with the secondary formations within the package needed to be studied farther. The Birozoan shell beds included in the Grimsby rather than the Cabot Head tell a story of depositional cycles and potential hiatuses, as well as the designation between the Grimsby and Thorold remains disputed. The Thorold boundary with the above Clinton Group formations tell a complicated story with the disconformity and hiatus told to us by the Densmore Creek phosphate lag. The Medina Group formations have had a complicated history with nomenclature. These definitions of these units have undergone numerous studies over the course of 150 years. Building upon that data to create more concrete geologic picks, future geologists can refer to the study for updated QA/QC protocols and physical pictures of geologic picks for reference. Not only providing formational rank descriptions, this study of the boundaries of the units can aid in the explanation of the depositional history of any units within the Appalachian Foreland Basin. This information can also be used for exploration geologists who target these formations for oil and natural gas plays and aid in the exploration of Ontario. This research was funded by several agencies: the Ontario Geological Survey, Natural Sciences and Engineering Research Council grant to Dr. Jiso Jin at the University of Western Ontario, the Ontario Petroleum Institute, and the Oil, Gas and Salt Resources Library in London, Ontario through the MITAC Accelerate program at Western. Special thanks goes to the staff at the OGSR Library for access to information, office use, and core photography. An extra special thanks go to my supervisors, Frank Brenton, Jiso Jin, and Al Phillips. Without them, I would be lost in Lake Erie somewhere. Their guidance and their thought-provoking questions about the Silurian stratigraphy of Lake Erie is a reason this thesis came to fruition. The fun part of geology is that you can send several geologists to the same outcrop and they will all have different answers. I welcome any questions and qualms with my picks, and I hope that you enjoyed my presentation. I will be available to answer any questions during the panel event after the presentation. Thank you.